This is the podcast for STEM Biology, Chapter 2, Section 2. This section deals with energy. A lot of that you learned with Ms. Hildebrand in physics last year. Remember, energy is the ability to do work. It can occur in different forms, like electrical, radiant, thermal, chemical, and mechanical. And in parentheses, there's an example. The energy that you see for biology would be radiant energy, because sunlight is important for life. You would also see it chemical energy, glucose for metabolism, and mechanical energy, which is energy inside organisms. Okay, we're going to watch this clip.
Energy is the ability to move or change matter. Energy exists in many different forms. A chemical reaction causes this bioluminescent click beetle to give off light energy. Heat energy causes ice to melt and water to evaporate. The swinging hammer has mechanical energy. Nerve cells use electrical energy to convey messages throughout your body. Stored energy is called potential energy. The man standing at the top of the diving board has a lot of potential energy. When he jumps off the board, the energy changes to kinetic energy, which is the energy of motion. An important characteristic of energy is that it can be converted from one form to another.
Energy and matter. There are three states of matter: liquid, solid, and gas. Adding energy causes the state change. In a chemical reaction, reactants are the substances that are entering the chemical reaction. Products are the substances that are produced by the chemical reaction. So if I give you an equation of two molecules of hydrogen plus oxygen yields, that's what you say for the arrow, two molecules of water. The reactants are on the left side of the arrow. That is what is needed for the reaction to occur. Water is the product, and that is what was produced by the chemical reaction. In this diagram, you can see that there are different types of reactions that deal with energy. On the left, it's showing an energy releasing reaction, where you start off with so much energy, and after the reaction is over, energy was released, like in the form of heat, for example. Another example on the right, energy was gained, and you can see that the energy was higher at the end of the reaction than at the beginning of the reaction. There's a type of energy that we need to talk about. It's called activation energy. Activation energy is the energy necessary for the chemical reaction to begin in living systems. If you add an enzyme, enzymes will lower that amount of energy that you need. They're also called catalysts. Catalysts reduce the amount of activation energy that is needed for a chemical reaction to take place. Enzymes in general, and we'll learn more about this in Chapter 3, are proteins, and they speed up metabolic reactions without being changed or destroyed. They are used over and over again. Okay, we're going to watch another clip.
The activation energy is the energy put into a system to start a reaction. While many reactions will proceed spontaneously, they still require a small input of energy to start. Matches, for example, burn, but only after energy is added through frictional heating caused by rubbing it on a rough surface. In other reactions, activation energy may come from heat, light, electricity, or any other energy input to the reaction system. Exothermic reactions require activation energy to start, but eventually release more energy than they consume. The energy given off as the product forms supplies the activation energy needed for the reaction to continue. Endothermic reactions require a great deal more activation energy. Although they also release energy, it is not sufficient to sustain the reaction without continuing to add activation energy.
Okay. Another term that we're going to discuss is oxidation and reduction. Chemical reactions in general transfer energy in living things. They involve the transfer of electrons. Reactions in which electrons are transferred between atoms are called oxidation reduction reactions. Here is an example that we're going to watch on YouTube. I'm going to click on it for you.
Alright, so this next reaction is the decomposition of potassium chlorate, which I've already put in our test tube. And all I'm going to do is heat the test tube to the point that the potassium chlorate melts, liquefies. And as the potassium chlorate melts, it will start to give off some of those extra oxygens from the chlorate polyatomic ion. And then that oxygen will start to fill the test tube, and as it fills the test tube, I'm going to take advantage of the fact that I have a very hot environment and a very oxygen-rich environment, and I'm going to add a gummy bear, for defensible gummy bear. And this squishy, sugary substance is going to react with that oxygen. A secondary reaction to the combustion of sugar. So the first reaction here is the addition of potassium chlorate into potassium chloride. Yes. Now that it's liquefied, you start to see some of that oxygen gas fill up the test tube. And then the second reaction, I'm going to take the oxygen gas that's liberated here and react it with the sugar in this little gummy bear, and just have a nice little combustion. Of course, combustion releases lots of heat and light, and this one also releases some sound. So now that my test tube is filled with oxygen, I'm going to move the flame away, drop my gummy bear in. Switch it a little bit so it'll fit. Oh! Get a gummy bear that'll fit. Gummy bear for 2-pack. There we go. We have 4 little parts of gummy bear flying out of the test tube. And now you can see why this is called the screener. And also why this test tube will never be able to be used again. So there you have it.
Okay, pretty cool. In that demo, this was the reaction. The sucrose, which was the gummy bear, has the formula of C12H22O11, was added to the oxygen that was released from the first reaction in the test tube. That yielded 9 carbons plus 3 carbon dioxides plus water. In this example, sucrose lost electrons. Sucrose lost electrons because it got smaller, it got broken down. Electrons were released. That means that sucrose was oxidized. Carbon gained electrons, and that was reduced. And that finishes our second section of chapter 2.